This is the recording of the tutoring session for June. Right. Alright, so before we start with the specific example, let's start with those formulas you were talking about. I have them pulled up here if you want.
Sure.
So these provide the illustrations of the triangles and the formulas that associate with them. So first thing I would do is like write on the board. I think I put it. Can I erase this?
Yes.
Rewrite dx over square root. So the first formula is if this is your theta and this is x and this is a. Oh, sorry, whoops. And this is a. Using the Pythagorean theorem, we get that this side is equal to x squared minus a squared. Oh, sorry, a squared minus x squared. My bad. And for this one, we know that x is equal to a sine theta. And that square root of a squared minus m squared is equal to a cosine theta. Does that make sense logically? So if we isolated this one, so if we know that cosine is equal to opposite over hypotenuse, cosine of this one is going to be like cosine of theta is going to be x squared to the square root of a squared minus x squared, and then cosine of but if we let's see, cosine of theta is going to be opposite. So that should be adjacent. My bad. Adjacent over hypotenuse. So that's going to be the square root of x squared over the square root of a. And then all we're doing is if we multiply that by a, we get a cosine theta.
Okay.
Is that much? Does that make sense? Okay. The only real thing you need to know that for is like sometimes when we solve out our equation, we're going to be left having to solve for theta, and this is how we do that.
Okay.
So keep that in mind. Okay. And I'm going to erase it because we can always redo that. But there's 2 steps using this. Second triangle we have to know is we have our theta here. We have a here, x here. Square root of x. So here we have that x is equal to let's see, it's going to be our opposite, so I think it's a sine. It's a tan. I'm sorry. Right. So the way we do that is cosine tan of theta, right, is going to be opposite over adjacent, right? So x over a, and we're just multiplying by a. So a tan theta is equal to x. Make sense? Again, then the last one you have to know is this triangle. Whoops, the cleanest. We have our theta here again. But now we have a and x at the top, and then this side is going to be equal to x squared minus a squared. And here, x is equal to a secant theta, and we can prove that the same way we did earlier. So if we look at here, secant theta is equal to 1 over cosine, and if cosine is adjacent over hypotenuse, it's going to be hypotenuse over adjacent. Make sense? And then a secant theta, you just multiply that and get rid of the x. Get rid of the a. Just exterior theta. So this is secant theta.
Yeah.
A secant theta
It's just
is just equal to x, and that's how we get that formula.
okay.
It's just flipped.
Oh, okay. I got you.
So the main reason we're doing this is to identify and define x in terms of theta for each of these triangles. Because we are going to have to substitute in x in our trig substitution intervals for these definitions in terms of theta to solve those and then resubstitute back into x. That's why knowing this is a prerequisite. But don't feel the need to memorize it right now because I know it's a lot of information. We can start with just writing that out and then like looking back at the formula while we're doing examples. So the
See you. And then,
do you want to start with your example?
Yeah.
Or do you want to start with an example I can give you?
Go with an example that you can give me, since I'm sure that it has like the steps.
Steps, yeah. Okay. So we can start with 1 over this will be 1 minus x dx. Okay, so the first thing we want to do is find out what interval, what like identity we're going to substitute in for x. Does that make sense? So I'm just gonna show you a trick. If it is, if it is a squared minus x squared versus a squared plus x squared versus x squared minus a squared, there are 2 or 3 different trig substitutions we can use. So, here, give me a sec. If we get that a substitution for, oops, sorry. Let me double check this. Yeah. There are a couple that we can use. So the first one is for a sine theta. This is if we see a squared minus x squared. And the reason this connects to the triangles is because we only use these identities for the funky like square root radicals we get on each of the branches. And then if you see an a squared plus an x squared, you're going to use x equals a tan theta.
Okay.
Oh, I'm so sorry.
My bad.
And if you see square root of x squared minus a squared, you're going to use a secant theta. Perfect. So, starting with our example again, sorry. We had 1 over 1 minus x squared.
It did not look like you.
Does this
I
look
cannot
like,
recognize if it was you
looks like
bent
a
over like that.
Sine theta.
yeah, it looks like a sine theta. So, we have So knowing this, right?
I was impressed.
For a squared minus x squared, this is x, right?
Mm-hmm.
So what is our a?
All right, just one.
Okay, a is just 1. And our x is equal to what?
X squared. What?
So x is actually equal to, so a sine theta.
Oh.
So if a is 1, x is going to be equal to sine theta.
Gotcha.
Makes
Okay.
sense?
Yeah.
Okay.
Oh, okay. Yes. Okay. I see what you're saying. Yes.
Does that make sense? Okay. So now we can do
She's like a little twig.
square root of 1. Oh, and now what else we have to do? We have to find d of x. Because we're substituting like u substitution, right? We have to put it in terms of the same variable. So if x is sine theta, what is the derivative of x?
Cosine.
So now we can plug all these into our integral. So 1 stays the same at the top. This becomes the square root of 1.
Do you need to keep the one, or can you just have that as? I guess you do.
You do need to keep the 1 because again we're just substituting our x here.
Okay. Oh yeah. I see. So it actually is like 1 minus 1 times sine theta.
It'd be 1 minus x squared. So the 1 minus here is the same as the 1 minus here.
Okay.
But the x squared is different. So if we know that x is sine theta, what is x squared?
X squared is going to be just sine squared theta.
Perfect.
Now,
Yeah.
if we didn't have like what a was equal to, would it just be? It would be in brackets, or in. It would be. Wouldn't no, a was equal to 1. Would it just be? Theta squared. Let's say like that wasn't equal to 1. A was equal.
No. So say for example we had this,
I just like clicked through the question.
and that means a is equal to 2, right? Because a squared, right? That means x is going to be equal to 2 sine theta. But this 4 actually stays the same. We don't get rid of it. So all we would have is 4 minus 4 sine squared theta. And the reason this 2 sine theta becomes 4 is because we're squaring the entire thing,
Okay.
right?
Yeah.
So the reason that's different is because now you get this.
Okay.
So you get a different coefficient, which changes your answer.
Okay.
So that's why the A specifically matters. Does that make sense?
Yeah, it does make sense.
Okay. But let's continue this, because I feel like after you get the first example down, it'll make more sense.
Okay.
So what this is testing is your ability to use a certain formula. I'm just going to tell you this as a step, as a getting step.
Is this arcsine or arctan?
Oh, sorry, we've got to plug in d of x, right?
Okay, yeah.
We know a certain formula using squares of sine and cosine, right?
Yeah.
Right?
Mm-hmm.
We're going to use this formula to simplify from 2 terms in a radical to 1, right?
Okay.
And you'll see why in a second. Just trust the process for right now.
Mm-hmm.
So, using these identities, what can we simplify 1 minus sine squared into?
1 minus 1 minus cosine squared.
I would just simplify it to cosine squared. Because 1 minus sine squared is equal to cosine squared,
Oh.
right?
Oh. Yeah. It's like effectively, yeah. That's what do we do?
But, I mean, yours is technically correct. It's just extra algebra.
Yeah.
So,
Yeah, you're right.
this is, I'm so sorry, I forgot the d theta. We need it. Oops. This then becomes 1 over the square root of cosine squared theta times cosine theta d theta.
Mm-hmm.
So now we have this radical. We want to get rid of it. We have the square root of a square number, so we can just get rid. They cancel out, right?
Yeah.
So now that term, square root of cosine squared, simplifies to what?
Just cosine.
Cosine. Now, do you see another way we can simplify this?
Yeah, it's going to equal 1.
Perfect. So, yeah, exactly, it just equals 1 d theta or just d theta. So now we know that the integral of a d whatever is just going to be like whatever that variable is, right?
Gotcha, so it's just going to be theta.
Perfect.
That's it?
So we're not done yet. Remember how I was like really insisted on like understanding the triangle part? We have to now transform that theta into like an x again, right? Because we want to solve it in terms of x. Put it back in terms of x.
Okay.
Okay, so if x is equal to a sine theta, how can we solve this identity to solve for theta?
We could. I don't know.
Let me walk you through it. So first thing we want to do is we're basically just isolating terms, right? From algebra. So we have the theta trapped with the sine, right? First thing I'm going to do is get rid of the a. Okay.
Mm-hmm.
And now we have x over a equals sine theta. Okay.
Mm-hmm.
Now I'm just going to do theta is equal to arc sine x over a. That's the easiest way to get rid of the sign. We just take the inverse of it.
Okay.
Does that make sense?
Mm-hmm.
And that may look really confusing, but I mean, in the pure math, it works.
Mm-hmm.
So you can just leave it like that and get your answer. You don't have to simplify. Unless your teacher specifies,
Mm-hmm.
you can just leave it in whatever confusing combo jumbo of arc sine, arc cos, whatever,
Mm-hmm.
because it is mathematically correct.
Okay.
So we have our theta here, the last step. We know what our theta is equal to, right?
Mm-hmm.
So, which is equal to arc sine, whoops, x over a
Mm-hmm.
plus c. Now we just have to plug in a, which is what?
A is just 1. So.
And that is our integral.
Okay.
So something you'll notice that's really common, you will have a lot of inverse trig functions in your answer.
Mm-hmm.
Because a lot of times you're substituting from x into a theta, and to get back from theta to x, you have to take an inverse of a trig. Usually, not always.
Gotcha.
Let's do your example next.
Okay.
Does that make sense?
Yeah, it does make sense. Alright. Let's see. If I stand up and do this.
Yeah.
So this one is just dx 9 plus x squared. And so really this just does equal 1 9 plus x squared dx. This should be a little confusing.
Yeah.
So first off, a is equal to
Alright, so,
a is equal to 3.
well, actually the first thing I would do,
Yeah.
we want to identify which formula it's using.
Okay, so it says plus, so we're gonna have
Perfect.
Okay.
Yeah. And again, like it may seem, if you get like x squared plus 9,
Mhm.
it's the same thing as 9 plus x squared, right?
okay.
So let's start with our identity.
So we're gonna be using. I'm just gonna say like use x equals a tan theta. So our a is going to be. Is it our a is equal to what 3? Or is it-
Perfect.
And our x is equal to. Our x is just equal to this.
Yeah.
Okay. X equals 3 tan pi, and then dx is equal to
think derivative of tan.
think derivative of 10.
Tan.
Tan. Oh, secant over cosine. Cosine, is that what it was?
So here, the derivative of tan is secant squared.
Secant squared. Oh my god, that's right. It's the easy one.
No, that's sine and cosine.
Squared. Pi. 3.
Yes, and we're forgetting one, and you're forgetting one. But yeah, first keep the coefficient. Perfect. Oh,
Oh no, d theta.
d theta.
Let's see. Okay. So this means that we can turn this from that into over. Did you move it down here? And like, did you keep the 9 when you were doing this?
Yes.
So you kept it 9 plus, then 3. This is also 9.
Yeah.
Okay, 9. Squared. 3. Secant squared. D theta.
Do you mind erasing this just so we can go down the next level?
Yeah.
Do you get it?
Yeah, I do.
I would just rewrite this thing at the top.
What's up? Mind if I sit over here? Yeah, go ahead.
5. 3.
Nothing, just, cybersecurity project for Friday, so that's what I'm kind of grinding. And then I found out that I have a stat assignment due tonight, so I gotta finish that first. I'm gonna go to that real quick. Need some water.
Okay.
I see you're watching something, so I won't.
From here we go. What is this? What is the
Key step.
key step?
So, after the substitution, we should do it perfectly. Remember what I was saying earlier about we want to get rid of this radical? So, I know it may be a bit tricky to see now. There's two identities we want to use. First, we know that we can take out 9 from here, right? So I would start by taking out 9. So
That is just 1.
oh, sorry, I would take out, it's the square root of 9, right? So it'll be, we have to take out 3 from the rest. So does that make sense?
Yeah.
Yeah.
So that's, we take out 3, 9 plus 10.
So actually, no. What I was thinking of, a way you can abridge the step is you can think of it like this. So if we have 9 plus 9, 10 squared theta, this becomes 1 plus 10 squared theta, right? And then that becomes 3 times 1 plus 10 squared theta. So what this is saying is like the only way you can take out a radical, something out of a radical, is if everything by that radical is multiplied. Everything inside the radical is multiplied by the same thing that you're taking out. So here we're taking out 3 because everything inside this radical is being multiplied by 3 squared.
Okay,
Right.
got you. That makes sense.
And like that way of like what I did of like fully illustrating it out makes it make sense. I hope, right?
Yeah, it does make sense.
Okay. So instead of taking out 9, we take out what? 3.
3 plus 10 squared. What is the arc of this?
I would also, just in case of public bias, I would replace the 1 with 3 secant squared theta d theta, since it's being multiplied by. You don't have to. I just thought it might be helpful. Rather than writing it to the side. Yeah.
Okay. there's 3's on both, so that's really just going to equal secant squared theta over
Exactly.
theta. Okay, the inverse of. So the inverse of the top is going to equal tan squared.
So no. So the
No,
inverse.
it's
So
tan.
if you remember that secant is equal to 1 over cosine. I think the next step. Okay, so the top. Next step we want to do is, like, if you remember to the old example, we wanted to get rid of the radical because we had a square trapped within the radical. So that's what I was saying. There's another identity we want to use that we can use to simplify 1 plus tan squared theta into a specific formula. I can pull it up here. So this is just a formula you have to learn for Triggs Hub, but it's similar to the sine cosine one. It's 1 plus tan squared x secant squared x.
Oh, okay. 1 plus squared x.
No. It's 1 plus tan squared x. Secant squared x.
Okay.
So here we see that. Now I want you to understand one thing. There's a difference between this formula and this formula. Here, sine and cosine add to 1, but here 1 is being added to 10. So a lot of times the way we see this expressed is as 1 minus sine squared x or 1 minus cosine squared x, okay? And then that we know we can say cosine squared or sine squared. Here, we will almost always see this as 1 plus tan squared x, because if you look at the identity we sub in, we will almost always get a positive number plus the same coefficient tan squared theta. But these two will change depending on whether you're subtracting a squared from x squared or x squared minus a squared. Does that make sense? So this is the key one to use for this identity. 1 plus tan squared x equals a tan theta. And that should be, I hope it's slightly easier to remember because the only one you use the tan thing for, the main one you use the tan thing for is if you have the tan substitution. Okay, so using this, let's try the next step. So we want to get rid of this thing in the radical.
Okay, so then that's going to be secant squared theta is equal to secant squared theta
It's just the teacher gives you better grades.
theta. So then this is just going to be equal to secant. Or
Secant theta.
This is just secant squared theta over theta.
Yeah, good catch there. A lot of students forget to take out they get rid of the radical and they keep the sign, the square, but it's good if you don't.
And then this is equal to what? Just secant?
Yeah. And then we're gonna have to integrate.
Yeah.
And another annoying part, we have to memorize the trig integrals. I have them pulled up here if you need them too. But secant x, no, secant x times. Oh, this one's so blurry. Oh my god.
Arc secant?
Let's say, why is it so blurry? Okay, here's one.
Okay. Wait.
Oh,
It's, we have secant. We could have it so it's
you have to memorize this integral. I'm not sure.
It's like everything.
Yeah, it's just this one. Yeah.
Yeah.
Okay. I don't know why we were getting such a weird one earlier. Let me double check. Integral of secant
That's like what
x.
always got me on tests. She would like take points off the notation and use some.
Yeah, okay, yeah. I just wanted to double check I was right. Okay, so this is just another formula I have to memorize.
Someone sent a girl from a sorority school to try out some of my dresses at 7, but she should try
Secant
it.
x
She should try it. Yeah, she should try it.
ln secant x plus 10x. Let's see. But we're almost there. So we just have to take our integral of secant theta and then plug in like into that massive formula. Oh god. What a mess. Ooh, what a good neck crack. You hear that?
Did hear that. Not think I was a negative. It sounded too nice. There's no way. There's no way. Space in between numbers.
Oof. We have the identity. We can integrate it. What are you looking for?
Just trying to see if it like says that anywhere, like right out in front.
I think if you have a formula sheet, it should be at the back of the book or the front of the book. General formulas.
Inverse trigonomic.
I think it'll be go back another one. I remember seeing that integral on like the trig integrals to memorize sheet. Oh, here it is.
No, I think this is all. Is this? What? It's just a massive.
Table of integrals. Whoa. Do we see one for trig?
Yeah, trig forms. Get it right. Secant x dx.
I'm like 1,000% sure it's this formula, Chris.
Okay.
I don't know why it's not just written out in simple English.
Okay.
Um,
So what? Next we go.
but next we want to integrate it from secant theta. So put that.
So now we have
Secant x.
theta.
Yeah.
C.
And now we have to do what?
Now we have to put it in terms of x.
Yeah.
Alright, so we go back all the way to the start. Is this? So we put it as x equals. How do we do that again?
We put it as you wrote it down here. X equals. So I would write out here. We have our identity. X equals a tan theta. Oh wait, replace the a with 3. Sorry.
No.
And now we want to isolate and solve for theta.
Okay. So this means that. So is this equal to theta? This is equal to theta? This. Okay. What am I feel like I'm lost here.
Okay, so let me help. You have two thetas here. you want to put those thetas in terms of x's, and there's two ways you can go about that. So remember I said the first way is usually you use this formula, you get an inverse trig function.
Yeah.
This is how you would do it. Okay. X equals 3 tan theta. X over 3 equal to tan theta.
Yeah.
Theta is equal to what?
Arc tan
On the right track. Finish.
x over 3.
X over 3. Okay, perfect. So what you could do then is plug this in. So you would literally do ln secant of arctan of x over 3 plus tangent of arctangent of x over 3 plus c. And I know that's a monster integral,
Yeah.
but that's correct.
Okay.
Like, absolutely disgusting.
What happens if he wants us to simplify them? Just
So there's two, yeah, you're absolutely right. My couch teacher actually wanted us to simplify it sometimes. Sometimes if you get something like this, you know this just simplifies down to x third, right?
yeah.
Other times, you're gonna have to use a triangle. This is where the triangle comes back in clutch, okay? Because you might think, why do I even need the triangle if I just know to use it's a squared, if I see this, use this, see this, use this, see this, use that, right? This is why. I'm gonna leave this answer up,
Yeah.
but
Just erase that. From the open space.
actually, we should have another. So we see we have secant theta, right?
Yeah.
We are gonna find what secant theta is on this.
Oh, okay.
Okay. So theta is. So what is secant theta equal to? Like, what is it the like reciprocal of?
Cosine over sine. Over sine. That might be right.
No, sine over cosine is tan.
Cosine over sine.
Cosine over sine is arctan. No, we don't. Cosine over sine is cotangent. Here, I'll show you.
Okay.
So secant is 1 over cosine, right? And cosecant is 1 over sine, right? So we know that secant is equal to. I'm gonna write capital S. Yes. I just want to save space. 1 over cosine. Okay. What is cosine equal to? Adjacent over hypotenuse.
Okay.
So this is equal to.
So it's equal to hypotenuse over adjacent.
Yeah, exactly. So secant theta is equal to hypotenuse over adjacent. Okay. This is our theta. This is our hypotenuse, and this is our adjacent. We would write ln secant theta is equal to, what is our hypotenuse? A squared plus x squared. What's our a? 3. So 3 squared plus x squared is going to be 9 plus x squared over a, which is 3.
Okay.
Don't confuse adjacent with a. It just happens to be that way.
Okay.
So we would write in substitute of not theta, secant theta. A plus x squared. Does that make sense? So the difference between the two methods, here, you're subbing in for arctan. So you will get ugly things like that. Here, you're subbing in for the entire trigonometric term. Okay, now we have to do tan theta. Tan theta is equal to what? Sokotoa, what is tan?
Can't be equal to. There's so much blood in my head. I'm sorry. I'm like trying to jump ahead. Kind of a whole lot. Tan theta is equal to just opposite over adjacent.
Yeah.
So, are you asking for like in terms of sine and cosine?
In terms of that triangle.
Oh.
So what is our opposite?
X over A.
So what is A?
Is equal to 3.
So this would be what?
3.
These two functions.
Okay, I was like concerned that it was something else. I was like trying to think really hard. I was like, oh, this is just
those two functions are equivalent.
Okay.
And the way you can tell, you can't easily tell this, but you can easily tell this. Tan of arctan cancels out. That get x is the same. So that is what you do if you need to simplify. You use the entire. So you use the triangle when you want to simplify.
Okay.
You use the identity if you want to keep it super long. Me personally, I know it looks crazy. I actually prefer this because while it's more work, it's easier. Like the best way to learn is by doing the problems over and over again. It's easy to shut the brain off and just write that entire thing out than think like that.
Yeah.
But I know like if you have to simplify it, you have to use the triangle.
Gotcha.
Does that make sense?
Okay.
And the reason I like shutting the brain off and doing this is because, again, this is correct. Like, this is mathematically equivalent to that. All right, do we have another example we want to do? We should have a little bit more time.
We can do a definite integral
Okay.
where it goes from -2 to 2.
I don't know if we have enough time to do the entire thing in 8 minutes, but are you okay if I guide you through it, or do you want to try it on your own? I'll help you real fast if you get stuck.
Just tell me real fast if we get stuck. 'Cause I am gonna get stuck. I feel like there's a lot of steps. Okay. So going from 2 to -2, it's 1/4 plus x squared dx.
Is that
So-
an radical or no?
No, it's not an radical.
Okay, got it.
So this is going to go to. I don't get it. So this is 4 plus. So it should be this. It's going to be tan, but it's not an radical.
Trick question. You still use tan.
Okay, cool.
It's just an example of where or it's just an example of where we use the same identity, even though it's not a radical. It just will look a little different, and that's okay.
Okay, so
So you want to get started?
yes, let's go for it.
Let's
so
do it.
A is going to be equal to 2.
Let's go. Oh, I would also erase that at the end. You can also just replace it, actually. Perfect. X is equal to.
Equal to A tan theta, and this is equal to 2. X is equal. Am I doing it?
Yeah.
Okay,
X is equal to a tan theta is equal to 2. X is equal to.
2 tan theta.
Yep.
This is equal to 2 secant squared.
Forgetting something.
Or d theta.
Yeah. Perfect.
That's right.
Okay. So let's go.
Okay,
So one more thing.
Yes.
Remember your bounds. What are they in terms of?
they're in terms of x.
So remember to write that. Remember like what I taught you for u sub?
Yeah.
X equals 2? Remember to do that.
Okay, so I'm gonna have, so it's still like this, is equals to, so 1 over, I wanna change it to this, right?
It's already in the form of that. Oh yeah, sorry. Yeah, you're right. I misspoke.
But this is just gonna look a little bit different, I just don't have the radical part, so it's just equal to, what is it? It's
4 plus.
4. Is it 4 plus? It should just be.
So that is the definition of x. So we have another term outside of our x squared.
Yeah.
So that stays the same.
Oh, that's
that is
gonna
not
stay
being
the same. That's right.
substituted.
Okay, 4 tan squared theta.
Oh no. So again, so we're subbing in the x equals a tan theta here. We have 4 plus x squared. 4 plus 4 tan squared theta. That's what it would look like.
Okay. I just have 4 plus. Okay.
So now I know it may look a bit confusing because we don't have a clear next step.
Oh, I need to have this in.
Yeah.
Oh yeah, I'll take that too. Yeah.
So now I know what I made it look a bit confusing. First thing, as I did last time, we want to simplify this into the terms we can put in the formula. So 1 plus tan squared theta. So like we did last time, get rid of the coefficient here and coefficient here, and take it outside of the interval.
Okay. So this is really 1/2. This is 1/2, right? X equals 2, -2. That's out, and then this is 2 tan squared theta, right? Am I doing this right?
Let me double check.
That's
No. So you had the right idea. This is 1/2, but not for the reason you think. If you did, I'm gonna avoid the bounds for the purpose of time. This is equal to, I'm gonna take out my 2 from the top, okay? Got it?
yeah.
This becomes 4 times 1 plus tan squared
Oh.
equal to 2 over 4 secant squared theta 1 plus tan squared theta. So that becomes 1/2, but you don't have a 2 in the denominator there. And again, you remember you need to keep your 1 plus. Because if you don't, it'll mess up the formula we had to use to get rid of that the 2 terms. Do you mind erasing the thing at the bottom?
Okay, so we have this.
I think last time, what did we do? It's a very similar situation.
We just took the inverse. We just did the integral.
Yeah.
So on the top it's gonna be tan over.
Whoa, no, sorry. So we used a formula to simplify this, right? Because we want to break it down into simplifying it further. What was the formula we used? Do you remember?
No, that's secant squared.
Yeah.
Okay, so this is secant squared over secant squared. There, this equals.
That looks like it simplifies it at the same time.
Simplifies the one.
Yeah.
So it's just 1
P theta.
d theta x equals 0 x equals -2. Okay, so the integral of this is going to be just theta.
Yeah.
So it's theta x equals 2 -2. So putting this in turn. Okay, so now we need to evaluate it at x equals.
So if you remember from last time, we want to put it in terms of x, right? Because our bounds are in terms of x, and
Yeah.
then we can evaluate it. So what was the strategy for putting it in terms of x? So there's no trig term, right? There's no secant theta, cosine theta, so this is useless, okay? What is the thing we can use?
Okay, what is this? What was the
Identity, perfect.
Yeah, so it's x over a equals tan
Theta.
theta. So it's arc tan, arc tan x over a equals theta.
Perfect.
Okay. So let's see. This is arc tan 2 over 2. Do I have to add a?
Incorrect. So I think you were perfect until there. So I would just simplify it like this: x over 2 to a -2, and then you're gonna get. So then evaluate it like that. Evaluate it if the form looks like that.
Yeah. That's what I'm trying to. That's what I was trying to do. I was doing it tan 2 over 2 minus.
That's why it's not just arc tan 2 over 2.
Yeah, it's working.
Oh, sorry. I thought you were saying your final answer was that.
No, I'm just evaluating.
Oh, I'm so sorry, Chris. My bad.
All good.
Okay. Yeah, I think that's it.
So really, this is just
Arcana 1 minus Arcana negative 1.
yeah.
Let's see. Good job.
Cool. That's it, man.
Wow, that was so lame. Come on.
See if we're on the camera right now.
That was on the
Let's
camera
do-
too. There we go.
My
High
bad.
five into a handshake. That was such an L. Alright. That is. Oh, and we finished right on time.
It works, man. Dude, did you mess up any handshakes with the people at the career fair?
Yes.
Nice. I had sweaty hands for a little bit. I was like,
Oh.
bro, I'm so sorry. I'm sweating right now, my friend.
Okay.